Have you ever wondered if life on Earth might have come from outer space? It's a fascinating idea and one that falls under the theory of panspermia. The word panspermia comes from the ancient Greek words pan meaning all and sperma meaning seed. Essentially, it suggests that life exists throughout the universe and is spread by space dust, meteoroids, asteroids, comets, and even by spacecraft carrying unintended microbial passengers. There are a few different types of panspermia: radiopanspermia, which involves radiation pressure spreading microorganisms; lithopanspermia, where life travels on rocks ejected from a planet; and directed panspermia, the intentional spreading of life by an advanced civilization. Each type suggests that microbes capable of surviving the harsh conditions of space could hitch a ride on debris from planetary collisions and travel across solar systems. This theory focuses not on how life began, but on how it might spread throughout the universe. Critics argue that it fails to address the true origin of life, merely shifting the location where life might have started. Moreover, it's challenging to test panspermia experimentally. Despite the criticisms, the idea has a long history, and some scientists are developing mathematical models to understand how life could naturally migrate through space. The theory has also sparked a lot of speculation and even hoaxes, especially following meteoritic events. So did life on Earth come from space? Could we all be cosmic travelers? While the theory of panspermia tantalizes us with the idea of life hitching rides across the cosmos, it also opens up another profound question. If life can spread so easily, why haven't we found evidence of it elsewhere? This brings us to the Fermi Paradox. Named after physicist Enrico Fermi, the paradox stems from a simple yet perplexing question: where is everybody? Given the vastness of the universe, with its billions of stars and potentially habitable planets, it seems statistically improbable that Earth is the only cradle of life. Yet, despite our efforts, we've found no definitive proof of extraterrestrial civilizations. This apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for or contact with such civilizations is the essence of the Fermi Paradox. Several hypotheses attempt to explain this paradox. One possibility is the rare Earth hypothesis, which suggests that while microbial life might be common, complex life is exceedingly rare, requiring a unique set of conditions that Earth fortuitously possesses. Another explanation is the Great Filter theory, proposing that there is a stage in the development of life that is extremely difficult to surpass, whether it be the emergence of life itself, the evolution of multicellular organisms, or the development of advanced technology. Some speculate that advanced civilizations might be deliberately avoiding us, adhering to a form of cosmic quarantine to prevent cultural interference akin to the Prime Directive in Star Trek. Others suggest that we might be looking in the wrong places, using inadequate methods, or that advanced civilizations are using communication technologies beyond our current understanding. The concept of the Fermi Paradox not only challenges our assumptions about life in the universe, but also pushes the boundaries of our curiosity and scientific endeavor. Are we truly alone, or is there a cosmic community waiting to be discovered? As we ponder the mysteries of the universe and our place within it, it's worth delving into the rich history of the panspermia theory. This idea, suggesting that life exists throughout the universe and can be distributed by meteoroids, asteroids, comets, and other celestial bodies, has captivated minds for centuries. The roots of panspermia can be traced back to the 5th century BCE with the natural philosopher Anaxagoras. Anaxagoras proposed that the cosmos was teeming with life, and that life on Earth began from these extraterrestrial seeds. While this early notion differs from our modern understanding, it set the stage for future explorations. Fast forward to 1908, when Swedish scientist Svante Arrhenius coined the term panspermia. Arrhenius argued that life had always existed somewhere in the universe. He proposed that bacterial spores could travel vast distances, propelled by the pressure of solar radiation. This idea gained traction among prominent scientists like Sir Fred Hoyle and Chandra Wickramasinghe, who suggested that life on Earth might have originated from space, carried by comets and meteorites. The 19th century saw significant developments that fueled interest in the origin of life. the Can't-Laplace nebula theory, Charles Darwin's theory of evolution, and the experiments of Louis Pasteur and John Tyndall, which disproved spontaneous generation, all contributed to the scientific community's focus on how life began. These developments led to two main theories: abiogenesis, the idea that life evolved from organic material on a primitive Earth, and panspermia, the idea that life came from elsewhere in the universe. Lord Kelvin, in 1871, proposed that life could be transferred to Earth by life-bearing meteorites, drawing parallels to how seeds are carried by the wind. Despite criticism and technical objections, the concept persisted. Arrhenius's work on radiation pressure provided a potential mechanism for the transport of life across the cosmos, though doubts about the survival of spores during such a journey remained. Hoyle and Wickramasinghe further advanced the theory by studying interstellar dust and suggesting that comets could carry the building blocks of life. They argued that viral material from space might have contributed to the evolution of life on Earth, a controversial idea that faced skepticism from biologists. Since the 1970s, planetary exploration has provided data to test panspermia. Though it remains a hypothesis, the theory's long history and enduring appeal underscore humanity's quest to understand the origins of life. As we continue to explore the intriguing concept of panspermia, it's important to consider the potential challenges and criticisms that this theory faces. First, there is the issue of survivability in space. While panspermia suggests that life can endure the harsh conditions of space, such as intense radiation, extreme temperatures, and the vacuum, we currently lack direct evidence to support this. The journey between celestial bodies is fraught with dangers, and the chances of survival for microbial life are still uncertain. Another significant criticism is that panspermia does not address the fundamental question of how life initially arose. The theory merely shifts the location of life's origin from Earth to elsewhere in the cosmos. Critics argue that this sidesteps the true mystery of life's emergence, leaving us with more questions than answers. Additionally, panspermia remains challenging to test experimentally. Retrieving samples from distant planets or comets to verify whether they contain extraterrestrial life is not an easy task. This lack of testability makes it difficult to gather conclusive evidence to support or refute the theory. The concept of contamination also raises concerns. If life did arrive on Earth via panspermia, it could have influenced our understanding of Earth's biology. This becomes especially relevant for future missions to Mars and other planets, where we must avoid contaminating these worlds with Earth life, potentially skewing scientific results. Lastly, the idea of directed panspermia, where intelligent civilizations intentionally spread life to other planets, is both intriguing and speculative. This notion raises ethical questions. Should humanity intentionally seed other worlds with life? And what responsibilities would we have if we did so? The ethical implications of such actions must be carefully considered. Despite these challenges and criticisms, the panspermia theory continues to captivate the imagination of scientists and the public alike.